Hi, we are going to look at section 4.1, which deals, we're going to go back to some graphing. And now what we're going to do is we're going to look at a couple of lines and we're going to see if these lines cross. And it's called a system of equations when you have two or more equations and you want to solve them so that you find a common point that works in all the equations that were given to you. So this list of equations, and we'll start with just two, are called a system of equations. Now, there are different methods of solving systems of equations to find that one solution, if any, that will work in both. And sometimes there's an infinite number of solutions that will work in both. Now, the first method we're going to talk about is graphing. There's also the addition method and the elimination method, or sorry, not addition, substitution method, and the elimination method, which we'll talk about in the next two sections. But this one is just on the graphing, just to give you a picture of what's going on and what we're trying to do. Well, we're going to start out here with a story problem, and I know that some of you don't like story problems, but you can, the more you practice them, the more you get used to them, and then you start to see a pattern within these story problems where they're all solved. Well, if you've got one of these, it's solved like this. If you've got a money problem, chances are it's solved like this. So you start to develop a pattern. All right, what we're going to look at here, well, we can just kind of look at the top of this note sheet. A system of equations is a set of two or more equations in two or more variables. We will try to solve these systems. That is, we seek to find points or point that work in all of the equations. And sometimes there's none. Okay, here is an example. The perimeter of an NBA basketball court is 288 feet. And you need to remember that in mathematics, each sentence, you've got a period here, each of these sentences is a standalone equation. All right. And so one of the things you need to do is try not to mix this one with another sentence. All right. Just each sentence, come up with an equation from each sentence. Well, I like pictures. So we're going to draw a picture of a basketball court. And we've got length and width. All righty. Doesn't matter which one's the L and which one's the W. It doesn't really matter. And I know that the perimeter of a basketball court is 288 feet. Well, the perimeter is the distance around if you were to walk around. So if this is L, and this is W, so they match, even though pictorially it doesn't. So our perimeter is L plus W plus L plus W. Now we're going to simplify that a little bit. Equals 288. Now, most of you are familiar with the perimeter of a rectangle because we added all of them around. We just went around and added them up. Is 2L plus 2W. I just combine like terms. So all of that came from the first sentence. And some of you may have just wrote this down right here. All right, without going through the whole process of where this comes from. And that's fine. That's just a basic perimeter equation. Okay, now we're going to leave that and we're going to look at the next sentence. The length of the court is 44 feet longer than the width, period. So let's talk about this, the length. So we're going to read this from left to right, and we're going to translate it from an English sentence to a math sentence. So doing this, we've got the length of the court is equal 44 feet longer than the width. So you would add, longer would be add. So that's my second equation. And really, that's the hard part, is coming up with the equations. The solving them you'll get better at, but that right there is the tough part. So now we're done with this section here, this top part. All we needed to do was to write a system of two equations that models this problem. Okay, so we've got the perimeter is 288 and the length is 44, longer, sometimes they say more than, W, the width. All righty, let's go to our next part here. We're going to use these equations. Using your system of equations above, check whether the following points solve the system. We say that a point solves the system if it works in both systems. What do I mean by works in both systems? It means that if you put in 94 and 50 here in for L and W, and 94 and 50 here, the left equals the right, the left equals the right. And we'll demonstrate that. That's what we mean by solve the system. It works in both equations. And in other words, when you put those points in, the left and the right are the same. Now, which is 94 and which is the 50? Well, if you remember, we talked that these are always in alphabetical order, always. So the 94 has to be the L, and the 50 will be the width. So let's go ahead and look at our first equation, and we're going to substitute that in. Here's our first equation. And I'm going to go ahead and write the other one right here. And all we're going to do is substitute in 94 and 50. And now this is a way for you to check your answers. When you find, you're going to be asked to find this point. And if you find this point, you can use this method to check the answer. All righty. So let's go ahead and go 2. The length is 94. The width is 50 equals 288. Awesome. So then when we multiply those together, 2 times this is 188. 2 times 50 is 100. And so you get 288 equals 288. So we're halfway done. It's true. That's true. The left equals the right. Let's put that same point into our other equation. They have to work in both, not just one. So you have to be careful of that. So we'll put 94 in for L and put in 50 for W. So 94 equals 44 plus 50 is 94. So yes, this point is a solution because it works in both of the equations when you substitute it in for those variables. All righty, let's look at these same equations and another point, 90, 46. Okay, so I'll just copy this down. 88, L equals 44 plus W. So we'll put in 90, alphabetical order. So we have 2 times 90 plus 2 times 46 equals 288. Is that true? We have 180 plus 92 equals 288. So we end up with 272 on the left, and we still have 288 on the right. Those are not equal. That is not a solution. And you could also put the 90 in here. You know, it might work in this one, but it's not a solution to the equation. If it doesn't do one, it's done. It's not a solution to the system. But we'll just go ahead. 86. So the answer is no. That is not a solution. Okay. But anyways, that's how you can check your answers. Here's an example of one that works, and here's an example of one that does not work. Okay, so let's go ahead and look at the box at the bottom of the page here and see what it has to tell us. Get some of my stuff out of the way here. I can move that up. There we go. All right, a system of equations is a set of 2 or more equations that are to be solved at the same time. So we're going to have 3 methods for solving them. Today is just graphing. A solution of a system of equations must make all equations true. Like this one. This is a true statement. This is a true statement, and they both must be true in order for it to be a point, in order for it to be a solution, that point to be a solution. Now, to solve a system of two equations is to find all ordered pairs or points or point for which both equations are simultaneously, are true simultaneously. Alrighty. So it depends on the equations, how many points of intersection you can have. So we'll kind of look at that idea as well. All right, let's look at some examples here on our next page. It kind of shows through the graph, so I wanted to put paper in between. All right, solving systems of equations by graphing. This kind of gives you a visual idea of what we're going to be doing. However, it's not the most accurate method of finding the solution. It's not the most accurate method. But we're going to go ahead, and it does give you a picture of what's going on. Remember, a graph of a function is the set of all points that satisfy the equation. So the graph is a picture of the solutions. Let's say we want to solve a system of two equations by graphing them. If we graph both equations on the same axis, then the solution to the system will be where the graphs overlap or where they intersect. Well, let's go ahead and go through an example. Now, solve the system by graphing. Now, when we were graphing inequalities, we were always solving for y, but these are not inequalities in this section. So you've got different methods of graphing depending upon what's given. You can use the x and y intercept method. That's usually the one I pick first. If it's in this form right here, the standard form. You can use the slope intercept method is another one, or you can use a t-chart, whichever one seems to work for you. This first one, I'm going to use the x and y intercept, and it's also a good review because you do have a final eventually coming up. To find out where it hits the x-axis, the y is 0. So if I have this right here, I should have made them further apart, but that's okay. I think it'll work. In order to find out where it hits the x-axis, the y is 0. It's gone. All right, so all we have is x equals 7. Because remember, when you want to find the x-intercept, you make the y 0. When you want to find the y-intercept, you make the x 0. So they're opposite. So we're going to find out where it hits the x-axis. And x equals 7. So we would have, I'll just go ahead and write this. We'll make the y 0. So x equals 7. So we'll go 4, 5, 6, 7 on the x-axis. And now let's find out where it hits the y-axis. We make the x 0. It's always the opposite. So to find out where it hits the y-axis, x is 0. So y equals 7. 6, 7. Awesome. All right, and now Pearson, you guys are lucky. Pearson's going to connect it up for you. So yay. All right. Oh, well, yeah. Well, that's not too bad. That's not too bad. Okay, now we're going to solve the next, we're going to graph, the next equation, but it's already set up in slope-intercept form. So rather than the x and y intercepts, we're going to use the slope-intercept. We're going to go to the intercept, which is always the y-intercept. Hits the y-axis at a -1. And then the slope is 3 over 1. You always put your whole numbers over 1 so that you have a rise over a run. You got to have that run. So we go up 3, 1, 2, 3, and over 1. So from the -1, 1, 2, 3, and over 1. And then we graph it. And for these, it should be pretty obvious what the solution is. Okay, so what point, now remember, these are pictures of solutions. What solution works in both of these equations is this point right here. And that point right there looks like it's the point 2, 5. Now you could check that. Put 2 and 5 into the top one. Sure, 2 plus 5 is 7. Put 2 here, and you get 6, because 3 times 2 is 6, minus 1 is 5, and that's a 5. So they work. So your solution to the system of equations is the point 2, 5. Ordered pair. And again, when you have these ordered pairs, you on Pearson, you've got to put the parentheses there. And sometimes they have one of the buttons is an ordered pair. You can just push it and put those in. All right, let's try another one. Now both of these, I'll probably use the X and Y method to graph them. Let's look. This one right here, in order to find where it hits the x-axis, y is 0. And the reason, why am I using this method? Well, because the numbers in front of these x and y both go into that number evenly. 1 and 1 both go into 3. So if it does without a fraction, I like this method. It's just easy. All right, so we're going to see where it crosses the x-axis, the first one. So y is 0. Divide by a -1. X is a -1. So the first graph crosses the x-axis at a -1. Okay, now also y minus x, to find out where it crosses the y-axis, the x is 0. And we're just left, we don't have to solve it like we did this one. We didn't have to finish it up. Oh, all right. I'm sorry, I've got to plug in my computer. Let me pause this real quick. It just sort of went very dull here. I'll pause it and all right, so I got that plugged in. So now we've got so here y equals 1, because to find the y-intercept, make the x 0. So we go up to the y-axis as 1, and we'll connect these up. I want to make sure that it's at least on the okay, well, anyways, that looks good. Since I'm actually interested in intersection point, I have to make sure that the graph is fairly accurate. Okay, now let's look at the next one. We're going to use the x and y intercept. I put the x first. And y plus x equals 3. We'll find out where it hits the x-axis. We'll make the y 0. We don't have to solve. We don't have to get rid of anything in the front. So x is 3. 1, 2, 3. To find out where it hits the y-axis, x is 0. Y equals 3. 1, 2, 3. So when we connect it up, here, the ordered pair that works in both equations seems to be the point 1, 2. So if you were to put 2 for the y, because y is 2, we're checking it. 2 minus 1 is 1. 2 plus 1 is 3. So it works in both equations, and this is a graphical solution. All righty. Now, every once in a while, we come up with some special cases here. And I think that will be this next one. Yeah. Okay, now the first equation, we're going to graph it. Again, we're still on this graphical method, graph the lines. So this one is the y-intercept method because we've got, it's already set up, the y is by itself. So we're going to go to 5 on the y-axis. There's our b, our y-intercept. 5. Now the slope is a -3 over 1. So we'll go down 3, 1, 2, 3, and over 1. And we'll connect it up. Here's my ruler. Awesome. That's close. Yeah, oh well, I probably should have moved it down a little bit, but hopefully we'll be able to figure it out. All right, now then this next one, I'm not going to use the X and Y intercept method because, like I did on the last two, because 3 does not go into a -2 evenly. So I'm going to make this one look like this one right here. So we're going to take Y plus 3X equals a -2, and I'm going to solve it for Y. Y equals, I'm going to put the 3X in front, the minus 3X, and the -2 behind. Okay, now we'll go ahead and we're going to graph it now. And again, you can't combine these. The 2 doesn't have an X. And the only reason why I put the 3X in front is so it matches the Y equals MX plus B idea. But if you put this and wrote -2 minus 3X, it's not wrong. All right, let's go to -2. There's our B. 1, 2. It's the Y-axis, not the X. Make sure you don't do that. This is always on the Y-axis. No, also a -3. So we're going to go down 3. And, oops, I'm going to put -3 over 1. From the -2 down 3. 1, 2, 3, and over 1. And we'll connect them up. Okay. Well, where do they intersect? Well, these lines are parallel, and parallel lines do not intersect. So what we have, we could have seen that by looking, okay, we have a slope of a -3, and our first one had a slope of a -3. So whenever their slopes match, we know that they will be parallel lines. And if they're parallel lines, there's no solution. If they are parallel lines, there's no solution. All right. Okay. Let's look at the next one. Now, the next one, it didn't turn out real well on my printer. Maybe it'll turn out better on yours. But this right here is a minus. This is a -12 plus 8x minus 24. We're going to go ahead and we'll graph these. Both of these, I will use the X and Y intercept method because 3 and -2 go into here. -12 and 8 go into a -24. I just think it's faster. So I'm going to go 3x minus 2x equals 6. Oh, sorry. 3y, not 3x. It does matter. All right, now to find out where it hits the x-axis, we make the y 0. So in order to solve this, you divide by a -2 both sides. So x then is equal to a -3. Okay, so we go to a -3 on the x-axis. So we made the y 0. Now to find out where it hits the y-axis, going through this a little bit quicker, hopefully you're good at it now, we make the x 0. So to solve this for y, you divide by 3, and 6 divided by 3 is 2. So we have our 2 points. We have a -3, 1, 2, 3, and a +2. Come up. Ooh. Mess with that. All right. Now the next one. Okay, to find out where it hits the x-axis, I'll make the y 0. So -24 divided by 8. To get the x by itself, you divide by 8. X is a -3. To find out where it hits the y-axis, x is 0. Divide by a -12 both sides. -24 divided by a -12 is 2. So we go to a -3 and we go to 2. Well, it just so happens that they're the same line. They're the same line. And what this means is that because they are the same line, they have an infinite number of solutions. So we have an infinite number of solutions. Any point on these lines, any point you pick will work in both of them, as long as that point is on the lines. So any point on this line will work in both. So if it happens to be the same line, we're going to come back and put different terms in for these, but it would be an infinite number of solutions. So there are times when you have one solution, there are times when you have no solution, and there are times when you have an infinite number of solutions. And as long as we're dealing with lines, those are your only two choices. You know, now if we have a cubic equation or a quadratic equation, we can have more than one. We can have like two or three. But for now, when we're just dealing with lines, which is all we're going to do in this section, you'll either have one solution, no solution, or an infinite number of solutions, depending upon what the graph looks like. All righty, great. Let's go. And what we're going to do now is we're going to attach a few terms, you know, and it's like a foreign language. And sometimes, you know, you need to know when they say the word independent, is it independent or dependent? Or they'll say it's dependent. What does that mean? Or consistent or inconsistent? So we're going to go through these, and then I'm going to give you a picture that'll probably help with differentiating these terms with the different solutions. But definition: when one equation in a system can be obtained by multiplying both sides of the other equation by a constant, then that means that the lines overlap. I didn't use the word overlap, I used the same line. Then the two equations are said to be dependent. If this is not the case, then the system is independent. All right, let's talk about that with an example. This right here. What do they mean if you can multiply one equation by a number and get the next equation? It's this. Or you can actually go through and solve it and see that it's the same line. Well, what number could you multiply this by and get this equation right here, match? Well, you could multiply by a -4, because then you get a -12, a +8, and a -24. So when that happens, if you can recognize that without going through the whole solution, if you can recognize, wow, if I multiply this by -4, it matches this one, number and sign both, on every term, I automatically know we have an infinite number of solutions. They're the same line. And we say that this is dependent. So when they're the same line, they're dependent. But if the lines are different, they're not, you can't multiply a number and have a match. If they're not, they're independent. And you could think of it as independent lines. So this is an example of independent. All right, so this is an independent line. Also, going back, let's put it over here. This one right here, these are independent lines if you have one solution. So this is independent. The one down below, this one right here, is independent. The lines are independent of each other. So the only time you have a dependent rather than an independent is if it's the same line. It's dependent. That's it. Okay, now we're going to attach another term to all of these, the solution. Consistent or inconsistent. So here, let's look at our definition, and then we'll go through the examples. We can see that if we are solving a system of two linear equations, there are three possible outcomes. We talked about that. The lines will intersect at exactly one point. This point is the solution to the system. Any system with at least one solution is called consistent. Here's the key, at least one. So you could have more. So what would be considered consistent? I'll draw a picture here. Okay. That is consistent. They intersect in one point. Also, if it's the same line, I'll put same line here. It's also consistent. So you can have at least one solution, maybe more. So these are called consistent. Inconsistent is no solution, parallel. All righty. So that would be the parallel. So we have consistent, consistent, and inconsistent. All right, and it kind of explains this in this one right here. Infinite number of solutions, this type is also consistent. If you have an infinite number of solutions, it's consistent. Let's go back and assign consistent or inconsistent to what we've done. So we know this is independent. It has at least one solution. So it's independent and consistent. Okay. Now, okay, so both independent lines and the consistent has got at least one solution. This one right here, one solution, so it's consistent. Okay. Independent lines, consistent, one solution. Okay. I'm trying to find my other example. I'm sorry. Oh. All right, this one right here is independent lines, but there's no solution, so it's inconsistent. So let's see. Yeah, this is my only one that's inconsistent. Yeah. But I guess you could think of it as they both have an I. So independent and inconsistent, both. All right, so there's no solution. And this last one, it's the same line. It's dependent and consistent. All right. And you can just kind of you can like maybe make some notes for a test if it's asked. All right, I'm not sure I'll ask it, but you can always just look at your notes until you get used to them. Okay, we're going to look at one more and then we'll be done. So we're going to solve graphically, then determine if the system is consistent or inconsistent, and if it is dependent or independent. But we're going to graph it first. And the reason why I really wanted to do this one is that here, we're going to go ahead and I can't use the X and Y intercept method. So I'm going to see, because 4 does not go into 9. So I'm going to go ahead and solve it for Y and see how that works out for us. So I'm going to take 4x minus Y equals 9 minus 4x minus Y equals a minus 4x plus 9. Divide by a negative 1, negative 1, negative 1. So we can graph it. We're going to use this slope intercept. Let's go ahead and get this one out of the way, and then we'll look at the other one. All right, so here we're going to go to a minus 9. Hopefully you have enough boxes. 6, 7, 8, 9, sure. Then we're going to go up 4 and over 1. 1, 2, 3, 4, and over 1. And connect these up. There it is. Okay. Close. Fully enough. Again, Pearson will do a great job of graphing yours, connecting your dots. Okay, now let's look at our next equation and see how do we want to graph this one? Well, I can see right now I can't use the X and Y intercept method because 3 does not go into 16, or -3 does not go into 16 as an integer. Now, if I solve it for Y like I did this one, minus X, divide by a -3, Y equals 1/3 X. It's 1/3. It's negative over negative is a positive. Minus 16/3. So we have an issue here because 16/3, these only go up in integers. In your Pearson, most of the time will only go up in integers. Sometimes it'll go up in quarters or halves. You just kind of have to watch that. All right, so how can I graph this? Well, I would like to look at the third method of graphing that we don't use very often, and that's a T-chart. And in order to fill in this T-chart, I'm going to use the original because I don't want to deal with 16/3. Nothing in me wants to deal with 16/3. I'm going to move it over. Excuse me. So we have X minus 3Y equals 16. And what I'm going to do, and this is the easiest, you just have to learn how to analyze these to determine what points I'm going to use for X and Y, is I'm going to put Y's in, because then I just bring it over and I have my X coordinate. Well, if I put in 0, let's say I put in 0 for Y. If this is 0, 3 times 0 is 0. So X, here, I'll just go ahead and put in 0. X equals 16. Unfortunately, my X axis does not go to 16. So I'm going to pick another one. How about maybe a -3 for the Y? So I will have X minus 3 times a -3 equals 16. X plus 9, because you multiply. Then you subtract 9. You just kind of play around with some numbers, and you end up with 7. Yeah. All right. So you have the point 7, -3. Can we do 7? Yes, we could. We could plot that point. Now, you'll find out that if you would have put in a positive for the Y, you end up with numbers bigger than 16, but you can try that on your own. Now, let's try another one. How about, I'll do it over here. How about a -4? Let's just try a -4. So we have X subtract 3 times a -4, substituting it in for our equation. So I'm using a T-chart. X plus 12, subtract 12, subtract 12. It looks like X is equal to 4. And that's another point that works with the graph that's given. So we'll plot 7, -3, 4, 5, 6, 7, 1, 2, 3. There's our 7, -3, 4, -4. 4. And there we have it. All right, so now I'm going to connect it up. Looks like we're going to go through that third point. That's kind of what I was looking at. Looks like it. So we do have a solution. What is that solution? That solution is 1, 2, 3, 4, 5. 1, -5, because we're down below. 1, -5. Now, if you were to put in a 1 and a -5, a 1 and a -5, you'll get 9 and 16. So it does work. Now, is this independent or dependent? Well, these are independent lines. So this one is independent. Let's see, where can I put, I guess I can just put it right here. So it's independent. Is it consistent or inconsistent? There is a solution, at least one. So it is consistent. All right, so we have a solution on these independent lines. It makes it consistent. And that solution is 1, -5. All right, well, if you have any questions on this, please let me know. Otherwise, I think we've covered everything that you should need for section 4.1. All right, bye-bye.